Okay. So n-queens problem is something that we saw before. So before we actually talk about the n-queens example, here is actually a way to organize answer set programs. So you don't have to follow this convention, but most often that this style of writing the program is like a programming idiom, helps you to structure the idea well. So it contains actually 3 parts. So generate, an optionally defined part, and the test part. For the first few examples, maybe most examples today, we are not going to use the defined part. We'll only use generate and the test part. And this is general idea about computer science, and as well as any problem solving. You want to generate possible solutions. And then you prune out among them which does not make any sense. So that the remaining thing is actually the solutions to the original problem. This is called generate and test paradigm. So the first part of organizing this ASP program is generate part. So we are going to generate a search space which contains a set of potential solutions. Now, not all the solutions in this space is actually the final solution. But this part contains at least all the correct solutions. It may contain some incorrect solutions, but for now, it's okay. The reason that we are doing this is actually it's easy to generate some potential solutions, and then we can prune out the best solutions later. As I said, there's an optional define part, which is to define some new atom in terms of other atoms. The test part is to weed out the elements of the search space that do not represent solutions. Okay? So this is the Queen's problem that we saw. The constraint here is no 2 queens can share the same row, column, or diagonal. Okay, so as you see, this is 8 by 8 grid, and there are 8 queens here. Okay, and we did this exercise before. When n equals 3, so there are 3 by 3 grid, then there's no way to place 3 queens on the board. Okay, so that no 2 queens attack each other. This is not possible. But if you go into n equals 4, we actually played it and found that there are 2 solutions possible. When n equals 5, there are 10 solutions possible. When n equals 6, surprisingly, the number actually goes down. There are only 4 solutions possible. When n equals 7, 40 solutions possible. N equals 8, 92 solutions are possible. So how do we generate all solutions? So what we are going to do now, what I'm going to do here is I will show you the English statement. Okay, and I'll give you some time for you to think how this can be formalized in the language of Klingo. Okay, and many of the exercises that we are going to do today is based on what we discussed last time. So one of the constraints in this domain is each row has exactly 1 queen. Okay, so if you look at each row, there is exactly 1 queen. Okay, so how can we represent this rule? By the way, what is actually the most similar thing that we did in the last class to represent some concept like this? Each row has exactly 1 queen. Did we do something similar last time? And what is that? What is this concept saying? There's a row and queen. What is the relationship between them? It's a function. If I give you 1 row, okay, this function returns the queen, where in the row that the queen is there. So this is a functional constraint. So here is how we are going to use. So we will first denote this position of the queen as queen of R, C. So when we see the atom like queen, let me just abbreviate as Q, 1, 2, this means there is a queen in the position 1, 2. 1 is the row number, 2 is the column number. Okay? Now what this rule is doing is R goes from 1 to n. Remember, n is any parameter that we can change. N could be 8 in the previous example. R goes from 1 to n. R here is a global variable, meaning that we are going to generate n number of rules, right? Are we together? Okay. And each of the row number R, we are going to select one column number from 1 to n. And you have to find exactly one of them. Okay? So for those who maybe forgot what we did last time, let me try to instantiate this rule. So R goes from 1 to n. So let's actually say n equals 3 because 8 is probably too much. So let's assume that n equals 3 for now. Okay? So first, you can see that the global variable will be replaced by global variable R will be replaced by 1, 2, 3. So if R equals 1, this rule, the first rule that you see, will give you 1, 1 dot dot 3. Okay? When R equals 1, this is what you get, right? When R equals 2, that's a good music. You get this. When R equals 3, you get this. Okay? Now, as I mentioned to you before, okay, try to instantiate as much as you can understand. Okay, so at this point, try to pause and see what is saying. The rule is saying that you have Q1 and you have data 1 data 3, right? And you have to select exactly one atom from there. So maybe let's actually do one more step. There is no local variable, but here we are using the interval. So when you have the atoms like this one, what does it stand for? It actually generates Q of 1, 1, Q of 1, 2, Q of 1, 3. This is just a shorthand notation for this rule, right? Okay, so I can also do the other thing, the next one, Q2, 1, uh, 2, 3, 2, 3, goes 1. Now, each of the rule is saying that among these three atoms, Q1, 1, 1, 2, 1, 3, okay, three possible positions for the queen at row 1, right? Queen, if the queen is at row 1, it could be either in 1, 1 position, or 1, 2 position, or 1, 3 position, right? Among these three possibilities, you have to choose exactly one. Are we together? Okay. What about the next one? So this one is saying that Q2, 1, for the row 2, there are three possible columns that you can choose. Same as the last one. For row 3, there are three possible columns that you can choose. How many choices are possible from the first rule? 3. You can choose 1, 1 or 1, 2, 1, 3. Okay, there's 3 choices. What about this one? How many choices for the second one? 3. How many? 3. So how many possible stable models are here? How many possible total choices are here? 3 plus 3 plus 3. 3 minus 3 minus 3. What is it? 9? There are 9 possibilities. 27. It's not working. So what about 4? What about 4? Can you place 4 in the first bucket? Can you place 4 in the second bucket? So what can we say about S of 2? So we cannot put 4 in, meaning that 3 is the maximum value that we can allow. So S of 2 equals 3. And I'm wrong here. S of 2 is actually not 3. What is the mistake that I just make? S of 2 equals 3 is actually false. But what I just did was I put 1 here and 2 there and then 3 there, and then I cannot put 4. Right? So it looks like 1, 2, 3 is the largest interval that we can place into 2 sum free sets. There's something that I deliberately did wrong. And what could be that? Yes?
Well, if you put 3 in the second bucket, then you
Aha. Good. If I put 3 here, then can I now place 4? Where do I place 4? In the first bucket, right? So now, without making 3 into the first bucket, if I choose 3 to be the second bucket, then I can actually add all 4 numbers. Good. Can I now try 5? Can I put 5? No. Is it because I did something wrong in the previous? It turns out that no matter what you do, you cannot put 5 numbers into 2 sum free sets. That's not possible. So from this you can conclude S of 2 equals 4. Now your turn. Okay. My next question is S of 3, and I'll give you some time to think about it. And you can talk with your neighbor if you want. So S of 3, I want you to think about this case. There are 3 buckets. And what is the largest interval? Okay? 1, 2, 3, up to what number n that you can place into 3 different buckets so that each bucket is sum free. Whoever gets the correct solution will get the participation credit. Oscar?
I think I got it.
You got it. What is your number?
13.
13. Anyone beat 13?
That's
16? Okay, 16 is a bigger interval. Anyone beat 16? So if 16 is true, we don't have to look into 13, right? Okay, let's actually look at 16 first.
I mean, I could be wrong, but that's very
Okay. If you're comfortable, then please come. If you don't feel comfortable, that's okay. Have another. 17? Sorry. There's a 17. Why does it come first? Yeah, we are talking about the largest interval, right? So if 17 is the correct solution, then that's it. Right? You want to? Right? Well, in the meantime, who is 17? No? Okay, so until then, we'll look at your solution. And this, yeah, this that one. Okay, 16. So 17, we go. So 16 may be next pole. You said 16, and I see.
Yeah, I did it. I did
Okay,
it a little more.
19 is maybe better. Okay, so why don't you step back and look at your solution. Okay, any doubt about this solution? Yes.
3 plus 7 equals 10 is the last.
3 plus 7 equals 10. Oh, this is not so 3. That. Well, thank you for trying. Okay, so 19 failed, 16, maybe not. Let's see, 13. Anyone beat 13 before Oscar tried? Okay, please sit down. Okay, so 13 numbers. So first, let's check whether we have all the 13 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so that's good. And then we have to check each set is free. Any doubt? Okay, so at this point, what can we conclude? S of 3 is at least 13, if this is true, right? Okay? We don't know whether this is the largest yet, because who knows, somebody may come with 14 people per solution. So what we just know so far is, based on what Oscar is showing, and looks like nobody has a counterexample to disprove, we can say S of 3 is at least 13. And in fact, it is the case. S of 3 is actually 13. So let me show you this table. Okay. So as you find out, that S of 1 equals 1, S of 2 equals 4, S of 3 is actually 13. This is not that difficult. The interesting thing comes from S of 4. S of 4 is actually known to be 44, and this was proven by Baumert in 1965 and Everett and Hansen in 1972. This is a paper that talks about S of 4 equals 44. Now S of 5, until a few years ago, nobody knew the value. S of 5 is proven to be in this interval. It should be at least 160 and at most 350, but until a few years ago, nobody could find the value. This is the result in 1979. It turns out that S of 5 is actually 160, which was conjectured to be the lowest number by Hu in 2017. Okay, S of 5 is 160. And that is this paper. And this paper is actually a very interesting one. The whole paper is to say that S of 5 is 160. Okay? Now if you look at the abstract, it says, we present solutions to a century-old problem known as theorem number 5. It's a century-old problem. Nobody could actually find the solution. How did he find? Okay, so we obtain solution 1 equals 160 by encoding the problem into propositional logic. We want propositional logic, right? Okay. And applying massively parallel satisfied with dissolving techniques of the resulting formula, we constructed validated proof of solution to increase the trust in the correctness of multi-CPU here computation. The proof is 2 petabytes in size and was verified using a formally verified proof checker. Demonstrating any result by certified solvers, no matter how large, can now be validated using highly trustworthy system. And it is conjectured in this paper that probably finding the value of S6 will be out of computing power at this point. Unless you have maybe quantum computing, it will be not possible to find this value. Okay? So if you disagree and try to use some techniques to find out, maybe you can publish your paper. S of 7 is known to be at least 1680. That was 2000 paper. The last one is actually the relation between Schur number and the so-called Ramsey number. There's another important number in the combinatorics. Okay, so we are going to solve this problem using Klingon. And how many rules do I need? I'm going to use 2 rules to solve this problem. Okay, what are the 2 rules? So as we know that we have to partition the interval 1 through k into 1 through n into k some free sets. So we have given 2 parameters, n denoting the size of the interval, and k is the number of buckets. Okay. All right. So our goal is to partition the set 1 through n into k subsets. We are going to use this atom in I, s to denote that the number I is in the set S. Okay, we will name the set as 1, 2, 3 as an integer. And also we are going to place the numbers 1 to n into this set. So if I say, for instance, in instance, in I 1 comma 13, I'm sorry, in 13 comma 1 means that number 13 is in the first cell. Okay? So how do we do that? Again, this is function. The function from what to what? Number to the bucket. If I give you any number I that ranges from 1 to n, this number, the integer I, should be mapped to one of the bucket, right? So how do we represent functions? We studied this multiple times. Domain, okay, is the global variable. I is the global variable here, and it represents the domain elements. Domain is from 1 to n. Okay? So for instance, for this problem, domain is 1, 2, 3, up to 13. And the range has 1, 2, 3. There are 3 buckets. How many possible functions are there? Where the domain is 1, 2, 3, up to 13. And the range is 1, 2, 3. How many functions are possible? If you get it right, I will give you another participation credit. 13 elements in the domain and 3 elements in the range. How many different functions can you generate? Okay, now opening the chance to one who already have the credit. You don't have to, right? What is the number of functions?
13 to 13.
13 to 13 is not close but not. 13. You can try everything possible, but that's not all of them. Brandon, this time?
3 to 13.
3 to the power of 13, yes, that's correct. Okay. Why is 3 to the power of 13? Why? Okay, if you don't, if you get confused about it, okay, think about this domain as 1 to 3 up to 13, right? The number 1 can be put into 1 to 3. So there's actually 3 choices, okay, for number 1, right? When and also 3 choices for number 2. The number 2 can be mapped to one of 1 to 3. And same for 1, 2, 3, and so forth. So each time you have 3 times 3 times 3 times 3 times 3 times 3 times 3 until 13 times. So the answer is 3 to the power of 13. Okay, so 3 to the power of 13 is a humongous numbers, right? So, but among them, okay, it may contain solutions like this, right? So what we did just so far is to put any number into one of the 3 buckets, right? That's what this line is about. Given the value, okay, I equals 1 to n. Each of the values, I, there is exactly one bucket associated with it. So this is a function from the number 1 through n into k buckets. Okay? It's the same structure as Queen's example. In Queen's, we have the row numbers, and then we choose exactly one column number. Same here. Okay? What is the relation? Here is a function from the number into the set. Meaning that for each number, we find exactly one set to be placed in. Okay? But if you do that, the set is not necessarily sum free, right? So we have to read out those stable model that has invalid case where the some set is not sum free. How do we do that? We want to say each subset is sum free. How do we do? We write this rule. Okay? If you have number I in the bucket S, also you have another number, maybe J, which may not be necessarily distinct from each other. But if you also have I plus J also in the same set, then this violates the constraint. Okay? So the first one is like this. The first rule is saying you are given the number from 1 to n. Just throw each number into one of the buckets. After that, you eliminate those cases where the set is not sum free. Then the remaining case is the solutions to the Schur number problem. Each set is sum free. And each set, the numbers from 1 to n is partitioned into k different buckets. Okay? So if you think this is a bit hard to grasp, that's true, because this is one of the notorious problems in the combinatorics. Okay? But I find this is quite intriguing. Okay? So it's a very small instance, but it actually blows up very quickly. Okay? And a lot of computer science problem is also like that. Like cryptography. Okay? It's a small problem, but it can blow up very quickly so that you cannot decipher clean coding. All right, so I'm going to show you how to run this code. And let me say this is the code that you have seen. And in order to use this code, I can type, I need to actually specify those parameters, right? So what is the n? N could be, say, 13, and k is 3. So that's the case that Oscar just showed. Okay, and file name is actually Schur number. Okay. So this is the solution that I get. In 1, 1 means the number 1 is in the first bucket. Okay, so let's actually look at what are the numbers in the first bucket. 1, right? Okay. 1 and 4, right? 4 is in the first bucket. 7 in the first bucket, and 10 is in the first bucket. Is it the same thing? 1, 4, 7. Actually, it's actually a different solution. Maybe there's more than one solution. Actually, that is the case. Okay. So there can be more than one solution, but it's possible to divide the interval 13. So in this case, what is actually the solution that we get? Let's actually write another solution that Twingo found. So 1. So look at the second argument that has 1. So that's this one. Okay, so number 1 is in the first bucket, 4 is in the first bucket, 7 is in the first bucket, and 10 is in the first bucket. So it's 1, 4, 7, 10, right? Okay. The next one is look at the second one. So 2, 3, 11, 12, right? 2, 3, 11, 12. Here. Now the third is 5, 6, 8, 9. 5, 6, 8, 9. Is that all? 5, 6. I'm missing one, right? 8, 9, 5.
It's 13 in the first position.
Okay, so 13 is actually here too. Okay? So this is also another possible solution. Actually, I wonder how many solutions are there? How many possible ways to partition this? There are 18 solutions. So we found, we just discussed 2 of them. Can this be actually 14? Because what Oscar and I just showed you is not that S of 3 is 13. It's just S of 3 is at least 13. So in order to verify that, let's try interval up to 14. And you see that it's not possible. No matter what combination that you try, this is not possible. Okay, good. That's interesting. Let's actually try something smaller. So when k equals 1, the Schur number was 1, right? Of course, that's the case. You put 1 in the first position. Can this be 2? Okay. Can Schur number 1 is 2? It's not possible. It says unsatisfiable. Now, if we increase the bucket, then of course we can put the number 1 and 2 into two different sets. And we can actually do this until 4. Okay? Can we do until 5? It's not possible. You cannot partition 1, 2, 3, 4, 5 into two sum-free sets. That's not possible. Okay, that's good. We just did S of 3, so that's fine. S of 4. S of 4 means we have 4 buckets. And do you recall what was the number for S of 4? 44, yes. So let's try 44. Okay, I don't actually need to generate all possible solutions. I only need to know whether there exists a partition, right? So let me just try only one. Okay, so we found one. Okay, so that is actually one. It's a lengthy list, but you can read it. So it takes only 0.3 seconds. So if you had Klingo in 1979, you could have published the paper. Not anymore, but. Can you see as 45? According to the theory, or according to the knowledge that we have, n cannot, S of 4 cannot be 45, right? Now, this seems to take more time than before, right? Because before we only find one solution and it was okay, but now we have to show that for all possible choices, that does not lead to any solution. But if we want to really say S of 4 is 44 using Klingo, we have to check this case. I don't recall how many minutes do I have to wait. So let me just stop here. If you're interested, you can try on your own. Okay. But what was S of 5? Do you recall? 160. Okay, so 160 is probably too much to do now. It will burn my MacBook. So let me try something else. So if k equals 5, I can try maybe 120. It doesn't take too much time. What I just checked is S of 5 is at least 120. To check it, it took me only 1.852 seconds. Not too bad. Maybe I can try 130. Should I do that? I'm not sure. It probably takes some minute. Well, let me stop here and let me just decrease it. 125. But this time, let me actually try to use thread. Okay, I can fork 4 thread and see, make them competing with each other. Okay. 125. One of the thread found solution in 1.7 seconds. Maybe I should try 130 now. So minus T4 means you can fork multiple threads, and each of them will try different branches. So it may find faster than just using one thread. Okay? But anyhow, this is actually a very difficult problem. All right, so we did until here. And as you notice, the Schur number SO5 is 160. This is not a big number. 160 is not really that big number. Right? However, it takes a lot of time internally. So this is a very interesting problem. Right? And the reason behind this is even though the number is small, there are a lot of branches that you have to consider. So when you do this 13 case, or 16 or 17, you have a lot of choices whether to put this number 30 in the second bucket or in the first bucket. Each of them leads to enormous branches. In fact, as I said, the total number of functions is 3 to the power 13. You cannot fit this number into reasonable size of the register. Okay, so this is one possible explanation why this is high. Okay, so let me stop here and let me open the subtractive. So finally it found solution in 55 seconds.